which covers sections from chapters 5 and chapters 4 and 5. Okay, so let's get started. Graphing exponential functions. Okay, say they give us to graph f of x equals to 2 to the power of x. This is an exponential function. So what we're going to do is pick values for x. Most commonly, the best values to use is like from -2 to about 3, or -2 to 2, something depending on the base, which is a 2. Okay, but most of the times are these numbers for x. So let's do our little table. Okay, now when x is -2, okay, all we're going to do is evaluate the function at 2. So we're going to plug in 2 for the x. -2 for the x. This becomes 1/4. So when x is -2, my y is 1/4. Now we're going to try -1. We're going to repeat the process from -2 to 3. So we're going to be evaluating at those the values for x. So when x is -1, we're going to plug in -1 for the x's. It's going to give us 1 over 2 to the power of 1, which will give us 1/2. So when x is -1, my y is 1/2. Now when it's 0, right? Anything to a 0 power is always 1. So 2 to a 0 power equals to 1. So when x is, y is 1. Now we're going to evaluate f of 1. Okay, which means it will be 2 to the first power, which will give us 2. So when x is 1, y is 2. Now we're going to do the evaluate the value of x at 2. So when x is 2, y is 4. And finally, when x is 3, we're going to find f of 3, which will be 2 to the third power, which will give us 8. So when x is 3, y is 8. And the graph will look something like this. Well, this is the actual graph. Okay. Now let's go to number 2. Graph the function f of x equals 2 to the power of x minus 1. So again, we're going to use the same values. But we're going to go all the way to 4 this time. Okay, right now I'm going to let you know why. So when x is -2, all we do is plug in -2 at the function where the x is. So it'll be 2 to the power of -2 minus 1 will give us -3, which will give us 1 over 2 cubed, which will give us 1/8. So when x is -2, y is 1/8. And if we keep repeating the process, right, this is going to give us 1/4. So when x is -1, y is 1/4. When it's 0, 0 minus 1 is -1. This is going to give us 1/2. And then when it's 1, 1 minus 1 is 0. So 2 to the 0 power will give us 1. When it's 2, right, it's going to give us 2 to the first power, which will give us 2. When it's 3, it's going to give us 2 to the second power, which will give us 4. And finally, when it's 4, it's going to give us 2 cubed, which will give us 8. Now this graph, I know I'm not going to graph it here, but let me go back. It's because it was real hard for me to graph it. Here in the PowerPoint. So what it does, it'll be the same graph as this one, but if you notice, all the values move 1 unit to the right. You see, so all these, you see, for example, when it's -1, right? Here on the first one, when it's -2 is 1/4, but now when it's -1 is 1/4. That means that every x value shifted 1 unit to the right. That's what it means. And then we graph it. Okay. Now these are all called exponential functions. So let's graph. This is also an exponential function. Let's graph 2 to a -x. So within the properties, this becomes 1 over 2 to the x power, which means it'll be 1/2 to the power of x. Let's see how this graph looks like now. Okay, again, we're going to plug in the values for x, right, from -3 to 3 now. So if we plug in -3, it's going to give us 2 over 1, right? Here, guys, when you have a fraction to a negative exponent, all you do is do the reciprocal, it becomes positive. So it's going to give us 8. Right? Then I'm going to repeat the process for all the x values. And then it's going to give us a -2, 4, -1, 2, 0, 1. 1 is going to be 1/2, 2 is going to be 1/4, and 3 is going to be 1/8. So this graph is called decay exponential function because it starts high and it goes low. Again, when x is -3, right? This is -3. My y is 8. When x is -2, my y is 4. When x is -1, my y is 2. When x is 0, my y is 1. When x is 1, it will be 1/2. When it's 2, it will be 1/4. And when it's 3, it's going to be 1/8. If you notice, it's useless to use numbers more than 3 because this graph is going to, it's going to get closer and closer and closer to 0, but it will never reach it. Okay, now, this is number 4 now. It says, how do we apply exponential functions in real life? Okay, so here's an example. It says the assets in billions of dollars for a Prudential Financial Incorporated can be approximated by the function a of x equals to 315 e to the power of 0.056x, where x equals 7 corresponds to the year 2007. So here it says find the assets for the following years, for the year 2000 and for the year 2012. Okay, so here's here, guys, this is crucial here where it says x equals 7. Right, so where x equals 7 corresponds to the year 2007, which means when x equals 0 has to correspond to the year 2000, and when x equals 12 corresponds to the year 2012. Okay, now, so for A part, we're going to evaluate it, right, at 0, because the year 2000 means that where x will be 0. So we plug in 0 for the x's. It will give us 315 e to the 0 power, which will give us 315. But this, guys, remember, it's in billions of dollars. So it's going to be $315 billion. Okay, now for B part. Okay, now again, this is good to know that 315 is called the initial value because when the time is 0 or when x is 0, the 315 or the number in front of the e of the e will be your initial value. Okay, it's good to know, I think, for the next problem that we're going to be doing. Now for B part, it says 2012. So we're going to evaluate it at a of 12, which means I'm going to plug in 12 for the x's on the exponent 0.05x. We're going to plug in the 12 there. So here, guys, right? So be real careful in your calculator, because if you plug it to the calculator and it gives you the space to put the exponent, then you're okay. But if it doesn't, then you have to put it with parentheses, because if not, you're going to get the wrong answer, because the calculator follows PEMDAS, order of operations. Okay, so this will give us 616.8171575. You round it off to the nearest 10th place. So it's going to give us something like $616.8 billion. Okay, now this is number 5 now. It states a deadly virus has infected the world. At the end of January, there were 2 cases, and by the end of April, the cases had grown to 128. It says find the model of the form f of t equals y naught b to the power of t, with t equals 0 corresponding to the end of the month of January. And then after you find the function or the model, then you use it to solve for part B. It says if the trend continues, about how many people will be infected by the end of the year. This is an actual problem that we came up with during the COVID. I think it was before spring 2020. before we went to lockdown, I used the information that was in the news, right, with the people being infected to come up with this problem here. Okay, so this is actually something that we can use like in real life. Anyway, how do we start? We need to find Y naught and B on the formula. Okay, Y naught is the amount present at time equals 0. So when they begin to when the values began, right, there were two cases. So A naught, Y naught means is equal to 2. Okay. Now that was by the end of January. Then by the end of February, T equals 1 because 1 month has passed. And then by the end of March, it'll be T equals 2 because 2 months have passed. And then by the end of April, 3 months have passed. So here's my by the last a few words on the question number 5. It says by the end of April, the cases have grown to 128. Okay, which means at the end of April, right after 3 months, there were 128 cases. So we're going to use the given info to find my B. Okay, we know that f of 3 equals 128, which means when t is 3, y is 128, or f of t is 128. So we plug in the f of 3 is 128. We have the y naught is 2, and the t is t for 3 months because 3 months had passed from the end of January to the end of April. Now all we do is solve for B. The first thing we do is divide both sides by 2. That will give us 64 equals to B to the third power. Now we're going to raise it to the 1/3 power, right? To cancel the exponent 3. But we're going to do it to both sides. You see on the right side, we have a power raised to a power, which means we multiply the powers. This way it will give us 3 times 1, 30 will give us 1, so B to the first power, right? That will give us B by itself. And 64 to the 1/3 power will give us 4. So we found our Y naught and we find our B. So all we do is plug him into the formula. Right, so this is the answer for part A. F of t equals 2, parentheses 4 to the power of t. You see, there's my Y naught, this is my B. Now, right now from the end of January to the end of the year, in December, it's 11 months. So we're going to evaluate f of 11 to see how many people were infected by the end of the year. This will give us 2 times 4 to the power of 11 will give us like 8,288,608 people would be infected by the end of the year. But I believe this wasn't the case because we use interventions like social distance and hand washing with sanitizers and all that stuff. That's what got. But if nature would have taken its course, about this many people will probably be infected. Okay. Now the next topic is solving exponential equations. Okay, we're going to be using this property here. It says let A be positive real numbers with A cannot equal to 1. If A to the power of U equals to A to the power of V, then the exponents must equal to each other. U must equal to V. Example, so we have 3 to the 5th power, 3 to the x power equals 3 to the 5th power. Then we apply the rule because we have the same base. So x equals to 5. Now we're going to solve number 6, solve for x. 125x equals to 5 to the 5th power. Okay, and we notice these are not the same base, right? Different bases. So we have to make him the same base. So we should be aware that 125 equals to 5 to the cube power because I'm trying to match the base, the 125 with the same base as the right side, which is a 5. So 125 equals to 5 cubed, so I'm going to replace 5 cubed for the 125. We've been on the exponent. Now we're going to use the power rule for the exponents, exponent power rule, which means when you have a base to a power raised to another power, you multiply the powers. You see, now we have the same base. Now we can apply the rule, which will give us 3x equals to 5. We divide both sides by 3, so x equals to 5 over 3. And you can always check your work. Okay, so I'm going to plug in x equals to 5/3 for the x's. Here, guys, you can use a calculator, or you can use the converting the exponent to a radical. Okay. You see, guys, you get the same thing, so I know that's the answer. Solving exponential equations continues. You see, if you notice, they get a little bit more challenging every time. Now we have 4 raised to the power of x minus 1 equals 32. Now, let's see if 4 and 32 share the common base of 4. So first, I'm going to do 4 to the second power. Right? It gives us 16. It's not 32. So let's try 4 to the third power and see what happens. No, it's over, which means the 4, they don't have the 4 as the same base with 4 and 32. So let's see, let's make it a 2 then. We know that by finding the common base of between 4 and 2, we know that 2 squared is 4, or 4 equals to 2 squared. And 32 equals 2 to the 5th power. You see, now we have the same base. So we're going to substitute 2 squared where the 4 is. Bring down the exponent, the x minus 1, equals, we're going to substitute 2 to the 5th power where the 32 is. Now we're going to apply the exponent power rule, which means when you have a power to a power, we multiply the powers. This is going to give us 2 parentheses x minus 1 close parentheses equals to 2 to the 5th power. Now we got the same base, right? So now we can apply the rule, which means 2 parentheses x minus 1 close parentheses equals to 5. We're going to distribute, right? Which means it's going to give us 2x minus 2 equals 5. We add 2 to both sides. It's going to give us 2x equals to 7. Divide both sides by 2. Gives us x equals to 7 over 2. Right? And again, we can always check our work. So let's plug in the 7 over 2 where the x is on the original equation. So it's going to give us 4 to the 7 halves minus 1 equals 32. So it's going to give us 5 over 2 equals 32. So if you put that in the calculator, guys, it's going to give you 32. So 32 equals 32, so I know that's my correct answer. Okay, now comes the topic of writing exponents, exponential equations into logarithmic equations and vice versa. Okay, now a definition of logarithms to the base a. If you have y equals to log of base ax, means a to the y equals x. This is called logarithmic form. Y equals to log of base a of x, and this is called exponential form. So we can go from logarithmic to exponential and vice versa. These are equivalent, but in different concepts. This is log on the left, and right. This is exponent on the right, exponential. Number 8. It says write each logarithmic equation into an exponential equation. Okay. So again, here, guys, we have to know what the a is, what the x is, and what the y is. You notice my a is equal to 9. My x is equal to 81. And my y is equal to 2. Now, now we're going to go from logarithmic to exponential. So it's going to be a, right, which will be 9 to the power of 2 equals 81. You see, there's my a, 9. There's my y is 2, and my x is 81. So these two are equivalent. Okay. Now let's go the other way. Write each exponential equation into a logarithmic equation. So again, right, we have to know what the A, right? So we're going to go from exponential to logarithmic. We have to know what the A, the X, and the Y are, right? The A is going to be 5. The Y is going to be 3. And my X will be 125. So it's going to give us 3 equals to log a base 5 of 125. See, there's my Y is 3. My A is 5. And my X is 125. Or you can do it, right? Or it can be log a base 5 of 125 equals 3. These two are the same. They're equal. Now, graphing logarithmic functions. Okay, in order to graph without a calculator, you must convert the logarithmic equation to an exponential equation. Okay? And here's my conversion. Example, graph y equals to log base 2x. This is going to be 2 to the power of y equals x. So there's my function, right? Now, instead of plugging in values for x, we're going to plug in for y because it'll be easier. Okay, we're going to do we're going to use the same values as what we chose for the exponential, but we're going to choose from -2 to 3. Remember, with exponential, we plug this in for the x, but now we're going to plug it in for the y. So we plug in -2 for y, it's going to give us 1/4. Right? So eventually, if we repeat the process as we did earlier, but instead of with the x, we're going to put in with the y's. This is my result here. When y is -2, it's going to be 1/4. When y is -1, again, it's going to give us 1/2. When y is 0, it's going to give us 1. When y is 1, it's going to give us 2. When y is 2, it's going to give us 4. And when y is 3, it's going to give us 8. Right? You repeat the process. Okay. And by the process, I mean, we will plug in here, for example, for the 1, we'll plug in -1, so it's going to give us 1/2, right? That's what it means right there. Now the graph, this is the exponential in blue, and the red is a log graph. This is like the parent function. Most of them will go something like this, right? And for the exponential, they're going to start low and go up high. Anyway, guys, that's how you graph a logarithmic function. The most important here is that you have to convert it from log to exponential in order to graph it. Now here, guys, I want you to expand or condense logarithmic expressions. Here are the properties. Number 1 is called the product rule. Number 2 is called the quotient rule. Number 3 is called the power property. They also are the same thing for the natural logs. Example, if you have log a base a of x times y, we expanded them, and it's going to be a plus in between. So it's going to be log a base a of x plus log a base a of y. And the same thing for the ln, which is a natural log. And for the log, right, this is for the quotient, log a base a of x divided by y. It's going to give us log a base a of x minus log a base a of y. And finally, for the power rule, right, if you notice, the power goes to the front. You see the r goes to the front. So if you have log a base a of x to the power of r, it's going to be r log a base a of x. Again, the power goes to the front. So it says here, write each expression as a sum and or difference of logarithms without variables to the first degree. Okay, now, so what rules are we going to have here? Or I mean, which properties, right? We're going to have the product and the exponential. So here, guys, right? Since we have a 5, an x, and a y, so it's going to be 3 different logs. We need to separate them. Right? That's where we apply the product property. Now, if you notice, the exponents, you can have no exponent, but it says to expand them, right? So you can have no exponent, so the exponent goes to the front. You're going to give log of 5 plus 4 log of x plus 3 log of y. Hey guys, if there's no base, if you notice there's no base here, it means it's base 10. Where there's no base, it's base 10. Again, here's the same properties. Here's another example. Here's a quotient rule. If you notice, right, we have all three properties. We have the product, we have the quotient, and the power. So first, let's start right with the quotient rule, which is if you have the quotient rule right, it's going to be subtraction. So it's going to be the top, which is the numerator, minus my denominator, right? There's going to be log of x, y squared minus log of w. Then we apply the product property, which means for the product, right, we're going to separate them. So it's going to be log of x plus log of y squared, and then minus log of w. Now we're going to apply the power property, which is the exponents must go to the front. It's going to be log of x plus 2 log of y minus log of w. There's your result. Can I just do one more? Here again, there's more properties. But this will be a little bit more challenging, right? No, it's not that bad. Now we're doing it with the ln. So again, from here, guys, we're going to be going from expanded to a single log or condense it. I believe in 1324, they call it single log, and in 1314, they call it condensed. So we have a minus, right? We have a minus. We're going to have the quotient rule. And since we have something in the front, we have the power rule. So first, right, we can apply, let the exponent go to the top. Like for example, right, the exponent here on the power property, the exponent goes to the top. And then we can apply the quotient rule. The subtraction means the quotient rule, which means right division. So it's going to be the ln of x plus 2 of x plus 7 squared divided by x plus 3. Now we're solving logarithmic equations. So we're solving, right? We got the same properties, but now we're going to be solving. Because remember, we were doing these to have them with the same base, but not every time you'll be able to get them to a same base, that they don't share a common base. So we can take the ln by sending the exponent to the front. Right? We bring down the exponent by doing the ln on both sides. Now we apply the property, the power property, and the exponent goes to the front. Then we divide both sides by the ln of 6. That's going to give us the ln of 72 divided by the ln of 6, right? We can put it in the calculator. And it's going to give us something like 2.386852,807. And most of the times, the instructor is going to tell you exactly what you rounded off to. Maybe it might be 4 places or 5 places. Here they wanted 4 places. So if it's 4 places, right, so we have a 38685. So 4 places, right, we always go to the 5th one. And in the 5th place is 5 or more, we add 1 to the 4th place, which would be the 8, we add 1. So that's why it's 2.3869. Okay, now, very important, guys. The ln of a number is an actual value. You cannot say divide by ln, right? Because that doesn't make sense. The ln of 72 is actually a number, and also the ln of 6. So be careful with that. You cannot separate them. Now, here we're going to be using some logarithmic properties in order to solve a logarithmic equation. And here's a property. If log of base AU equals to log of base AV, if you notice there's a single log on each side of the equal sign, then the U must equal to V. For 15, on the left side, we have a single log. But on the right side, we don't have a single log. So we have to use our properties to put the right side as a single log. Right, since it's minus, is going to be the quotient rule, which means we have log of x equals to log of x plus 3 over x minus 1. Now, right now we can apply the rule. So it's going to give us x equals to x plus 3 over x minus 1. Here, guys, we can cross multiply or multiply both sides by x minus 1. So it's going to give us x times x minus 1 equals to x plus 3. Now on the left side, we're going to distribute. So it's going to give us x squared minus x equals to x plus 3. Now, since we have an x squared, we have to set the equation equal to 0. So we're going to subtract negative x minus 3 to both sides. That gives us a 0 on the right side. But on the left side, if we have x squared, negative x minus x will give us negative 2x, and we have the negative 3. Now we have to factor or use a quadratic formula. In this case, right, I know we can factor it. So this will give us x minus 3 and x plus 1 equals to 0. If you guys have a hard time factoring, look at go view the workshop that we did in week 3. It's about factoring. And perhaps you have a better idea how to factor. So we said both binomials equal to 0. So it's going to give us x minus 3 equals 0 or x plus 1 equals 0. It's going to give us x equals to 3 and x equals to negative 1. Now we can always check our work, right? But I mean, a heads up, guys, the ln or the logs cannot equal to a negative value or also to 0. They have to be more than 0. They have to be positive, okay? Because if you put log of negative 1 in your calculator, it's going to give you error. So first, let's check the negative 1. Right, so we're going to plug in negative 1 where all the x's are. And here, guys, if you put that in the calculator, guys, it's going to give you error, which means it's not defined. So that cannot be the answer. Now let's try the 3. But we're going to plug in 3 for all the x's. Right? Now here, guys, we can actually use a calculator, or we can use the properties. Let's see if we can put them as a single log. Because remember, on the right side, right, we can put this as a single log. If it's minus, it's going to be the quotient. So it's going to be log of 6 divided by 2. So we got log of 3 equals log of 3, which is correct. So the 3 is the correct answer, solution. Let's try another property with the logs. Now, for this property, if you notice, right, we want to cancel the log of 4. We don't want it there. Okay, so how do we do it, guys? So by using this property, the log of 4 of 5x plus 6 becomes your exponent, and we put a big 4 as a base. Right? When you do to the left side, you also do to the right side to balance the equation. Now on the left side, right, by using the property, the 4 base 4 raised to the power of log base 4 of 5x plus 6, the base 4 with the log of 4 base 4, they cancel. So they go to 1. So by applying the property, it's going to give us 5x plus 6 equals 4 squared. 4 squared is equal to 16. Now we're going to subtract 6 from both sides to solve for x. Now we're going to divide by 2. I mean by 5. I was thinking about the answer. So x equals to 2. I'm sorry about that. So the value is 2. And again, you can always check your work. I'm going to plug in 2 for the x, which will give us 16. Right, and then on the left side, this is, you can use the change of base. Right, I believe I went over that. I think in week 5 or 6. Right, if you put log of 16 divided by log of 4, it's going to give us 2. So 2 equals to 2. So we know that's my correct answer. Now comes chapter 5. This is the simple interest problems here. Okay, now there's different formulas, guys, for each set of problems. For the simple interest, we have a different formula. For the compound interest, also a different formula, and also for the annuities. So in this case, this is a formula, future value equals to present value, 1 plus RT. Right? So it says here, Gabriel invested his summer earnings of $3,000 in a savings account for college. The account pays 1.5% simple interest. What will be the value of this account after 2 years? And how much interest did he earn? Because here, guys, what are we looking for? We're looking for the value in 2 years. So we're looking for the future value. So the 3,000 has to be the present value. The R is going to be the interest rate, which will give us 1.5%. Convert that to a decimal, will be 0.015. You always move the decimal place 2 places to the left, and you drop the symbol. Or you can divide 1.5 by 100 and drop the symbol. It's going to give us 0.015. And the time has to be in years. And here, guys, this is 2 years, so t equals to 2. So what we do is plug into the formula, right? Use your calculator, and we get 3,090, which means that the value in 2 years of the account will be 3,090. Okay, now how much interest did he earn? So for the interest is equal to the future value minus the present value, which means the value that they got in 2 years minus what you initially invested. So it's going to give us 3,090 minus 3,000 will give us $90. That's how much interest Gabriel earned. So after 2 years, he had 3,090 in the account, and the interest earned was $90. Now comes compound interest. Okay, for compound interest, this is a formula that you use, but for simplification, to plug into the calculator, it's better to use this one here. Future value equals to present value, 1 plus R divided by M times MT. If you notice, the second formula is future value equals to PV, 1 plus I to the N. The I is equal to R divided by M, and the N is equal to M times T. Okay, and here's what everything means. The future value, FV, means future or maturity value. The PV stands for principal or present value. The R stands for the interest rate per period, convert to a decimal. The M stands for number of compounding periods per year. The T stands for the number of years. The I stands for R divided by M, which is the interest rate per period. And N is equal to M times T, which is the total number of compound periods. And here are the keywords for compounded. If it says yearly or annually, M is equal to 1. Bi-yearly or semi-annually, M is equal to 2. Quarterly, M is equal to 4. Monthly will be 52. Will be 12, I'm sorry. Weekly will be 52. Daily, it depends. It'll be 365, but at times the book wants you to use 360. If they don't specify to use 360, they use 365. If it's continuous, it'll be a different formula. This will be your formula. Future value equals to present value, e to the power of RT. Here's where we can use these type of problems. These compound interest can be used to invest a certain amount of money without depositing additional money into the account. What you do is invest, like say whatever you want, 10,000, and then you leave it there for 2, 3, or 4 or 5 years, right? Without touching the money. And this is a formula that you use. Okay, let's give a scenario here. You deposit 9,000 in an account at your bank that pays 2.5% interest semi-annually. How much money will be on your account after 10 years? How much interest did you earn? Okay, this can be like a real-life scenario. Say that you have $9,000 that you can spare, but you don't need them. So let's say you go to the bank and you want to set up an account where you deposit the 9,000 in a compound interest account. They're going to give you 2.5% compounded semi-annually for 10 years. Okay, my formula. So there's going to be 7 things that you need to know. Here, guys, we're looking for the future value, right? Because it's saying how much money will be in the account after 10 years. So we're looking for the future value. So the present value is 9,000. The interest rate they offer you is 2.5%. Converted to a decimal will give us 0.025. The M by compounded period will be 2 because it's semi-annually. The T time will be 10 years. The I will be R divided by 2. 0.025 divided by 2, which would be 0.0125. And the n will be m times 2, will be 2 times 10, will give us 20. So all we do is plug into the calculator, everything there in the calculator, right? I mean, plug all the values in the formula, use the calculator, and you get, I believe, $11,538.34. Round it out to your nearest penny. So for 10 years, there will be $11,538.34. Now for the second part, how much money did you earn in interest, right? Because you only put in 9,000 and you got more than 11,000. So how much did you earn? So we use interest earned equals to future value minus present value. So we subtract the 9,000 from what you got in 10 years, and it's going to give us $2,538.34. So this money is how much interest that you earn, the $2,538. Now comes another type of problem here. This is called the future value of an ordinary annuity. So it says here, and for this one, guys, it's going to be a different formula, okay? And right now, I'll put the formula down. At the end of each quarter, a 50-year-old woman puts $1,200 in a retirement account that pays 7.2% interest compounded quarterly. When she reaches 60, what will be the value in the account, and how much interest will she earn? So this is a different formula. Here's your formula, right? So we're looking for, see what we're looking for. When she reaches 60, what will be the value in the account? So we're looking for the future value. So the payment that she's making is $1,200, right? And the interest rate is 7.2%, which you give us 0.072. Compounded every quarter, so it'll be 4. For how long? Hey guys, here they don't give you the time, right? But with the given info, you can get the time. When the lady was 50, right? She started this account. Then when she reaches 60, that was her goal, and which is 60, right? Which will be in 10 years. See how much money she will have in the account. So T will be 10. The I will be R divided by M. 0.072 divided by 4 will give us 0.018. And the N is 4 times T will give us 40. So all we do is plug everything into the calculator. Okay. Let me show you how you will put it into the calculator without stopping it on a steady flow. So you will enter the numerator into the calculator. Parentheses 1 plus 0.018 close parentheses to the power of 40 minus 1. And this is what you should see on the screen in the calculator. 1.04, 1320, 138 on the screen, right? Then you're going to hit the division key because you're dividing what you just got by 0.18, right? So this is what you get. So then you're going to divide, press on the division key, and that's what you see on the screen. Then you're going to enter the 0.018. After you do that, this is what you should see on your screen. 57.85111.879. Right, and this is what actually is taking place. Now you're going to hit the multiplication key, and this is what you should see on your screen. The answer times, right? That's what you should see, and then you're going to enter the 1,200. And finally, guys, this is how much money rounded off to your nearest tenth, right? Which you give us 0.34. So it's going to give us $69,421.34. This is how much money will be in the account after 10 years. But how much interest did she earn? Okay, how can we find that? If you notice, she paid $1,200, right, for 40 times. 40 times, she made 40 payments of $1,200. So we're going to multiply the 40 times 1,200 will give us 48,000. So the rest, right? So she earned 69,000. So, but this is how much money came out of her pocket. So to find how much money did you invest, right? Right. So how much money? So how much interest did you earn? So right. So we subtract the 69,421.34 minus the 48,000. So it's going to be like $21,421.34. That's how much she earned in interest, which is not bad, right? Okay, now the last one, number 20. Because this is going to be also the present value of a no-new annuity. And again, this is a different formula. This formula is used to purchase like a real expensive item, like a house, like a car, something that's real expensive, and you're going to borrow the money and then you're going to make payments. So here, guys, if you notice, it's a different formula than the previous one. For the last 4 problems, every single one had a different formula. Okay, now you want to purchase a house that costs $325,000. Because the $325,000 is the money that you're going to borrow from the bank. That means you need that money now, right at the present value, because you're going to go to the bank and get qualified, and this is the amount that you want. So that's going to be my present value. What you're looking for are the monthly payments. So the present value that you borrow will be $325,000. The R will be 3.9% divided by, move the decimal place 2 places to the left, or divide that 3.9 by 100 and drop the symbol, right? It's going to give us 0.039. The M is going to be 12 because it's monthly payments. The T is for 30 years. So the I is going to be R divided by 12, 0.039 divided by 12 is going to give you 0.00325. The N is M times T, which would be 12 times 30, and that'll be 360. Also, the end, guys, so this is the number of payments that you make, 360 payments. Now let's put everything into the formula. Because if we notice, we're starting for the payment, right? So I'm going to show you how to put it into a calculator in a steady flow. So first, you're going to enter the numerator, which is 1 minus parentheses 1 plus 0.00325, close parentheses, raised to the power of negative 360. And this is what you should see on the screen. 0.68904,36901. Now, right now, you're going to hit the division key. After you do that, this is what you should see on your screen. Answer divided by. Now, you're going to enter the 0.00325. You can enter. You should see 212.0134431. Right? Now, you're going to hit the inverse key. Why? Because we're starting for the payment, right? So you're going to hit the inverse key, and that one is where it says x to the negative 1. You're going to press on that key. Then this is what you should see on your screen. Then you're going to enter the 325,000. And this is what you see on your screen. 1532.921664. You're going to run that out to your nearest penny, which will be 1532.92. So these are your payments, $1,132.92. Okay, how many payments did you make, right? So we made 360 payments. So I'm going to multiply the monthly payments by the total number of payments, which is 360 times 1,532.92. It's going to give us $551,851.20. Okay, now how much did you end up paying for the house? Right? We only borrowed $325,000, but you end up paying over $500,000. So to see how much money you paid extra in interest, is going to be $551,851.20 minus $325,000, which will give us $226,851.20. That's how much money you end up paying extra. Because to eliminate all this interest, what you can do, if you can afford it, you pay extra money every month into the principal. And this way, you can pay a lot less interest and end up paying the house in less than 30 years. Well, students, this is it for this exam review. I'm so happy that you guys came into to this workshop, and let me take it back to the host so they can tell you of upcoming events.
Next week, we will have system of equations. Thank you so much to Professor Albert Isasi for presenting today. Thank you to the audience for coming and being a wonderful audience, and we hope to see you soon again. Thanks.